Hello and welcome to the Moonlit Physics. Before we dive in, make sure to like this video and subscribe if you haven't already, so we can continue wandering together through the fascinating landscapes of the universe. And while you're settling in, I'm curious. Where are you watching or listening from right now? Perhaps you're cozy in your room, gazing at the night sky, or maybe you're on a train quietly moving through the world. Wherever you are, it's interesting to think that even the simple act of knowing your own local time connects you to the wider cosmic rhythm. After all, time itself is not as steady as it seems. Your seconds might be ticking slightly differently from someone else's, depending on where you are and, as we'll soon explore, even how gravity surrounds you. Tonight, we're venturing into a question that stretches across both the human mind and the cosmos. How does gravity actually make time run slower? Seconds that seem ordinary here on Earth may behave very differently near a massive star or a black hole. Time, which feels so familiar and uniform in our everyday lives, is in fact elastic, bending and stretching in ways that are almost unimaginable. We'll journey from the ticking of your own biological clock to the warped space-time around massive cosmic objects. Along the way, we'll meet groundbreaking scientists, uncover less-known theories, and peek behind the curtain of reality to see what truly governs the flow of moments. So get comfortable, let your mind drift gently, and let's begin this exploration of time, not just as we experience it, but as the universe itself measures it. Time is often imagined as a river, flowing steadily and uniformly, carrying every moment from past to future without pause or deviation. Yet, as we begin to explore the universe in greater detail, this simple picture begins to unravel. Time is not a single, straight line, but a flexible and multi-layered phenomenon, capable of stretching, compressing, and twisting in ways that challenge both intuition and imagination. Our everyday experience of seconds, minutes, and hours gives the comforting illusion of consistency, but the reality of time is far more intricate, shaped by the deep architecture of the cosmos, the motions of matter, and even the processes of our own brains. In physics, time is intertwined with space itself, forming a continuum that is sensitive to mass, velocity, and energy. In everyday life, this influence is imperceptible, and the seconds tick as we expect, gently guiding our routines and the rhythms of our lives. Yet, on cosmic scales, or in the presence of intense gravity, those same seconds may stretch into hours, or contract to fractions of their usual duration. Gravity, far from being a mere downward pull, subtly warps the very fabric of space-time, bending both the paths of objects and the flow of time itself. This is a notion that, at first glance, can feel almost fantastical. The familiar and measurable moments of our lives are not immune to the immense forces that govern the universe. We will be weaving together multiple perspectives in this exploration, drawing on conventional physics, speculative theories, and cognitive science. This means considering not only the elegant equations of general relativity, which describe how mass curves space-time, but also the forward-thinking ideas of scientists like Ilya Prigozhin, who studied dissipative structures and the emergent, irreversible nature of time in complex systems, and Lee Smolin, whose research into cosmological time evolution imagines the laws of physics themselves as dynamic and evolving rather than fixed. These insights reveal that time may not be merely measured, but generated, emergent, and context-dependent, a tapestry woven from interactions, motion, and change. Even at the level of human perception, time is far from uniform. Our minds actively construct the flow of seconds, guided by attention, memory, and prediction. While a mundane wait may stretch endlessly, moments of joy, wonder, or novelty often vanish in the blink of an eye. Neuroscientific research shows that circuits in the brain, including regions such as the suprachiasmatic nucleus, basal ganglia, and prefrontal cortex, work together to produce this temporal narrative. These biological clocks and predictive mechanisms overlay a personal sense of time upon the physical progression measured by clocks, allowing our conscious experience to vary independently of universal time. Gravity adds an additional layer of complexity to this tapestry. Massive bodies such as planets, stars, and black holes warp space-time in their vicinity, causing clocks to tick at different rates depending on their proximity to these gravitational sources. In the 1970s, experiments like the Haffel-Keating flights, which carried atomic clocks aboard commercial airliners around the world, confirmed that time measured by moving or differently situated clocks does indeed diverge ever so slightly, just as Einstein's equations predicted. On Earth, these differences are minute, fractions of a second, yet near a neutron star or black hole, the effects become profound, illustrating that time itself is malleable, shaped by the cosmic stage upon which events unfold. To truly appreciate the flexibility of time, it helps to consider the universe on its grandest scales. Stars live and die over millions or billions of years. Galaxies dance and collide over spans far exceeding human comprehension, and the observable universe stretches across approximately 13.8 billion years of history. Within this vastness, our everyday moments are fleeting, yet they remain part of a continuum that stretches across space and time, subtly influenced by the forces that govern the cosmos. The elasticity of time, once considered merely a curiosity of science fiction, is an essential feature of the universe, affecting everything from the evolution of galaxies to the decay of particles in a laboratory on Earth. High-level concepts like emergent and relational time challenge even further the notion that there is a single, absolute now. Julian Barber, for instance, suggests that the universe consists of a series of snapshots, or configurations, with the flow of time arising from the relationships among these configurations rather than from a universal current. Carlo Rovelli, working in loop quantum gravity, extends this view, proposing that time emerges from the interactions between systems rather than existing independently. In both cases, what we perceive as moments unfolding is a construct, a relational pattern arising from the interplay of matter, energy, and observation. From these perspectives, even the moment you're experiencing right now, the tick of a second, the sensation of the present, connects to a vast and dynamic cosmic landscape. Each heartbeat, each breath, each conscious observation is part of an intricate web in which physical laws, biological mechanisms, and relational patterns converge to generate the passage of time. It is this profound flexibility that makes time both scientifically fascinating and deeply personal, a phenomenon that is at once measurable, felt, and in some sense, created. As we begin our journey into the depths of gravity, space-time, and perception, it is worth holding this complexity in mind. Time is neither a simple river nor a metronome ticking independently of the universe. It is a fluid, multi-layered experience shaped by cosmic forces, cognitive processes, and emergent structures. In understanding how gravity can slow time, we begin to glimpse the richness of the universe itself, seeing that every moment, every second, and every tick of the clock is part of a far greater, beautifully intertwined system, stretching from the circuits in our brains to the curving edges of space-time around distant stars. And so, as you settle in, allow yourself to follow these ideas gently, letting your curiosity drift across scales both vast and intimate. Time, it turns out, is far more elastic than we ever imagined, and the universe is ready to reveal just how fluid those seconds and minutes really are. Our experience of time is profoundly shaped by the brain, an organ that does far more than passively register seconds and minutes. Neuroscientists such as Mark Whitman, who studies interoception and the way bodily signals inform our sense of duration, and Patricia Churchland, whose work in neurophilosophy explores how consciousness arises from neural activity, reveal that the flow of moments is actively constructed rather than simply observed. Time, in this sense, is both subjective and relational, molded by attention, memory, and expectation. Every glance, every heartbeat, every subtle shift in focus contributes to a continuous narrative that we experience as the present. At the smallest scales, neural processing occurs in microseconds and milliseconds, temporal intervals so brief that our conscious awareness cannot directly perceive them, yet they are crucial for integrating sensory input and generating a coherent experience of continuity. Neural oscillations, particularly in the theta and gamma frequency ranges, act as internal pacemakers, coordinating activity across distant brain regions to create a stable sense of temporal order. These oscillations allow the brain to link events, to bind stimuli into sequences, and to maintain the feeling of flow even as individual sensory signals arrive at slightly different times. In effect, the brain produces its own local time, an internal rhythm that can stretch, compress, or even pause relative to the external clock. Attention plays a central role in shaping our subjective experience. When we focus intensely on a task, seconds may pass unnoticed, slipping by almost imperceptibly. Conversely, during moments of boredom or discomfort, minutes can stretch endlessly, each tick of a clock feeling unusually long. Researchers have found that this phenomenon arises not simply from perception, but from the way attention modulates neural processing and memory encoding. The more novel, emotionally significant, or unpredictable an experience, the more densely the brain records it, and the longer it feels in retrospect. David Eagleman, a neuroscientist at Baylor College of Medicine, has demonstrated this effect in controlled experiments, showing that sudden threats or unexpected stimuli can make very brief events seem to last much longer than their objective duration. Memory intertwines closely with attention to shape the sense of elapsed time. The hippocampus, a deep structure involved in episodic memory, encodes sequences of events, linking them to spatial and contextual cues. The prefrontal cortex helps maintain temporal order by integrating attention and predictive processes, allowing the brain to anticipate what will happen next and adjust its internal model accordingly. Together, these systems generate a coherent narrative, a stream of experience that feels continuous and fluid, even though it emerges from discrete neural events that are individually measured in fractions of a second. Interestingly, these cognitive mechanisms mirror certain principles observed in physics. Just as gravitational time dilation causes clocks near massive bodies to tick more slowly, our brain's processing of moments can expand or contract relative to other experiences. In both cases, time is not absolute. It depends on context, interaction, and observation. This parallel is not purely metaphorical. Cognitive, local time, and physical time dilation share a fundamental similarity. Both demonstrate that temporal flow is relational rather than universal, that the passage of moments is influenced by position, motion, and perspective, whether within a neural network or a curved space-time continuum. Even mundane activities reveal the elasticity of our subjective experience. Walking through a bustling city, our attention constantly shifts from one stimulus to another, and each interval of time is experienced differently depending on focus and expectation. A conversation filled with novelty and laughter may feel to last mere minutes while objectively spanning hours, while waiting in line for a task we do not enjoy can seem interminable. This everyday malleability echoes the findings of researchers studying extreme or unusual conditions, such as astronauts in orbit or sensory deprivation experiments, where temporal perception diverges markedly from objective measurements, highlighting how context and internal processing shape experienced time. The brain's construction of time is both predictive and adaptive. It continuously integrates incoming sensory data with past experience and anticipatory models to generate a sense of continuity. Predictive coding, a framework developed by Carl Friston and further explored by Anil Seth at the University of Sussex, describes how the brain anticipates what is likely to occur and adjusts its internal model based on discrepancies between expectation and reality. When predictions align with reality, time appears to pass smoothly and effortlessly. When events are surprising or mismatched, the moment may feel drawn out, highlighting the flexibility inherent in neural timekeeping. Our subjective experience of time also depends on physiological signals from within the body. Heartbeat, breathing, and other interoceptive cues act as internal reference points, anchoring perception and influencing the perceived duration of events. Mark Wittmann's research suggests that interoceptive signals are critical for temporal awareness, providing a rhythm that the brain uses to gauge the passage of moments. These bodily rhythms, integrated with neural oscillations, create a multi-layered temporal structure in which both milliseconds and minutes contribute to the seamless flow we experience as the present. Taken together, these insights show that time is far from uniform within our own minds. The perception of now is not merely a reflection of external clocks, but a rich construct, emerging from the interplay of attention, memory, neural oscillations, and bodily signals. It is an internally generated rhythm, dynamic and adaptive, that allows humans to navigate complex environments, make predictions, and coordinate behavior effectively. In this way, cognitive science reveals a parallel to the physics of time. Both demonstrate that moments are relational, dependent on context, and far more flexible than our intuitive sense might suggest. As we consider how gravity can stretch or slow the passage of time in the cosmos, it is instructive to remember that our brains, in their own way, perform a similar function. They bend and shape the flow of seconds, milliseconds, and microseconds to create a coherent, meaningful experience. From the flicker of a neuron to the orbit of a planet, Time is never a simple, uniform backdrop. It is a layered, dynamic process, intimately tied to observation, interaction, and the networks, whether neural or cosmic, that give it structure and meaning. For centuries, the idea of time was simpler, almost comforting in its regularity. Isaac Newton, in the 17th century, described time as absolute, flowing uniformly and independently of events, matter, or observation. He imagined it as a steady, invisible river, a universal clock ticking reliably throughout the cosmos. In this framework, every second, minute, and hour marched forward at exactly the same rate for all observers, everywhere, whether on Earth, atop a mountain, or traversing the solar system. Newton's vision of absolute time provided the foundation for classical mechanics, allowing scientists to predict planetary motion, the fall of objects, and the trajectories of projectiles with extraordinary precision. Newton was not alone in shaping this perspective. Pierre-Simon Laplace, a French mathematician and astronomer, expanded on Newtonian determinism, imagining a universe so perfectly ordered that, if one knew the positions and velocities of all particles at a given instant, the entire past and future could be calculated with certainty. This deterministic worldview painted a cosmos governed by strict cause and effect, where the unfolding of events followed from the immutable laws of physics. In such a universe, time acted as an impartial stage, a backdrop against which all processes could be measured and understood. The practical utility of Newtonian time is remarkable. Engineers, astronomers, and clockmakers have long relied on its consistency to design bridges, calculate the orbits of satellites, and synchronize human activity. In everyday terrestrial conditions, from driving across continents to cooking a meal, absolute time is sufficiently precise, giving the sense that seconds tick uniformly and reliably. Even today, the calculations used to send spacecraft to distant planets often begin with Newtonian approximations before relativistic corrections are applied. For most human purposes, this framework works so well that it can feel as though time truly is a fixed and universal quantity. Yet, as we peer deeper into the universe and probe phenomena at extreme scales, cracks in this classical view begin to appear. Newtonian mechanics does not account for the finite speed of light, nor does it explain why electromagnetic waves propagate independently of the observer's motion. It assumes an omnipresent, immovable clock, yet observations in the 19th century, including the famous Michelson-Morley experiment, suggested otherwise. The concept of hidden variables, parameters that might exist unseen, governing the behavior of particles and systems, emerged as a way to reconcile determinism with the uncertainties revealed in these experiments. While Newtonian physics could describe the predictable movement of billiard balls or planets, it struggled with light, high speeds, and gravity's more subtle influences. Absolute time also fails under conditions of intense gravity. Near massive bodies like neutron stars or black holes, Newton's simple river of time cannot account for the slowing of clocks predicted by Einstein's general relativity. A second measured on Earth is not equivalent to a second measured near a black hole, even if the same kind of atomic clock is used. Classical models assume that forces act in isolation, that motion and mass operate linearly, and that time progresses uniformly. In reality, the universe is far less forgiving. Under extreme velocities approaching the speed of a light, or in regions of highly curved space-time, Newton's approximations give way to the more nuanced framework of relativity. Despite its limitations, Newtonian and classical time remain indispensable for building intuition about the world. They allow us to understand momentum, energy, and motion in predictable terms, and provide a stepping stone toward deeper concepts. While a particle may follow probabilistic rules at the quantum level, or a clock may tick differently near a massive star, the classical notion of time teaches the principles of causality, measurement, and temporal consistency that are still embedded in modern science. Recognizing these limitations sets the stage for a richer understanding. Time is not a simple, absolute entity, but a relational and observer-dependent phenomenon. It is a concept that, when explored beyond the surface, reveals elasticity and context dependence, bending and stretching according to motion, mass, and perspective. As we move beyond classical models, we begin to see time not just as a backdrop, but as a dynamic fabric, intimately connected to the very structure of the universe, awaiting exploration through the lenses of relativity, quantum mechanics, and the curious workings of our own minds. Imagine travelling through space at a speed approaching that of light, leaving Earth behind. As you journey farther and farther, a curious thing happens. The passage of time for you slows relative to those who remain behind. This is not science fiction, but the reality predicted by Albert Einstein in 1905 through his theory of special relativity. Special relativity introduced a radical idea. Time is not a fixed universal measure, but depends on the observer's state of motion. The faster you move relative to another observer, the slower your clock ticks in comparison. One way to visualize this is through the classic thought experiment known as the twin paradox. Imagine two twins, one staying on Earth while the other embarks on a journey in a spaceship moving close to the speed of light. Upon returning, the travelling twin will have aged less than the twin who remained on Earth. This is not a trick or a mathematical oddity. It reflects the fundamental relationship between relative velocity and the flow of time, a consequence of the constancy of the speed of light for all observers. Even mundane motions at everyday speeds produce imperceptible effects, but as velocity increases toward the speed of light, these differences become measurable and undeniable. While Einstein formulated the theory, less cited contributors like Hermann Weyl played essential roles in shaping the mathematical framework. Weyl's work on gauge theories, for example, helped formalize how forces and symmetries relate to spacetime structure. Friedrich Kottler, another mathematician and physicist of the early 20th century, contributed to the development of coordinate systems capable of describing events in a relativistic context. Their insights, though less widely known than Einstein's, were crucial in refining how scientists represent and calculate phenomena in moving frames of reference. A particularly useful tool for visualizing these concepts is the Minkowski spacetime diagram, named after Hermann Minkowski, Einstein's former teacher. These diagrams map events in 4 dimensions, 3 of space and 1 of time. By representing motion through this combined framework, it becomes clear how simultaneity is relative. 2 events that appear simultaneous to one observer may occur at different times for another, depending on their relative motion. Lines representing the paths of objects, known as world lines, reveal how the passage of time stretches or compresses along different trajectories. Through these diagrams, abstract equations gain a tangible geometric form, making the effects of velocity on time easier to grasp. Special relativity also demonstrates that time dilation is not merely theoretical. Experiments involving particles in accelerators moving at significant fractions of the speed of light confirm that these particles experience slower decay rates relative to stationary observers. This is a direct manifestation of time slowing down due to motion. Even satellite systems, including those used for global positioning, must account for these relativistic effects. Though the velocities involved are modest compared to light speed, the accumulated discrepancies would translate into navigational errors of several kilometers per day if left uncorrected. The link between relative motion and time dilation can be expressed mathematically in the familiar form of the Lorentz factor. When a clock moves at velocity v relative to an observer, the elapsed time for the moving clock relates to the observer's time tt as t equals t divided by the square root of 1 minus v squared divided by c squared, where c is the speed of light. This equation encapsulates the counterintuitive but experimentally verified principle that motion affects time itself. As v approaches c, the denominator approaches 0, and time for the moving clock slows dramatically relative to the stationary observer. These effects underscore a profound departure from classical Newtonian intuition. Time is no longer an absolute, flowing at the same rate everywhere, but a dimension that bends and flexes according to relative motion. The principles of causality remain intact, but simultaneity, duration, and the very measurement of seconds are now dependent on perspective. This realization prepared the ground for the next layer of understanding, the interplay between time and gravity, where massive bodies influence not just the path of objects, but the rate at which time itself unfolds. Through special relativity, we begin to see that our perception of a uniform and universal time is a convenient approximation, suitable for everyday life, but not a fundamental property of the cosmos. Each observer carries a personal measure of time intertwined with their motion and position, much like a localized river flowing at its own pace. As we venture further into the theory of general relativity, these insights serve as a stepping stone, illuminating the path toward understanding how gravity, mass, and energy can warp this river itself, creating regions where time bends and slows in ways that challenge even our most basic intuitions. In this light, time is no longer merely a measurement, but a dynamic participant in the structure of reality, responding to motion and context. The seconds and minutes we take for granted are, in essence, malleable, stretching and contracting as the universe itself dictates. It is a humbling and fascinating revelation. The familiar flow of time, so deeply ingrained in our experience, is just one perspective among many, dependent on the frame of reference, the velocity of the observer, and the hidden geometry of space-time around us. In the presence of massive objects, time behaves in ways that are far more subtle and profound than anything suggested by Newtonian mechanics or even special relativity alone. Albert Einstein's theory of general relativity, formulated in 1915, revealed that gravity is not merely a force pulling objects together, but the manifestation of curved space-time itself. Mass and energy warp the fabric of the universe, bending the paths of planets, light, and even the flow of time. When a clock is situated near a massive body, it ticks more slowly relative to a clock further away, a phenomenon known as gravitational time dilation. This effect is not hypothetical. It is measurable, consistent, and integral to our understanding of the cosmos. Einstein's formulation of general relativity was influenced and supported by important collaborators, including Marcel Grossmann, who helped provide the tensor mathematics necessary to express the curvature of spacetime, and David Hilbert, whose work on the formalization of the gravitational field equations complemented Einstein's insights. Together, their contributions enabled the theory to move beyond abstract thought and into precise, testable mathematics, allowing scientists to predict and verify the effects of gravity on both motion and time with remarkable accuracy. One striking example of gravitational time dilation occurs in everyday life, though imperceptible without sensitive instruments. Atomic clocks, which measure time with extraordinary precision, run ever so slightly faster at higher altitudes, where the pull of Earth's gravity is weaker than at sea level. The difference is minuscule, mere nanoseconds per day, but it accumulates over time and must be accounted for in systems like the Global Positioning System. GPS satellites orbit roughly 20,000 kilometers above Earth, moving both rapidly and through a weaker gravitational field than the surface. Engineers must correct for both the velocity-based time dilation predicted by special relativity and the gravitational time dilation predicted by general relativity. Without these adjustments, positional errors would grow at a rate of approximately 10 kilometers per day, rendering navigation systems unreliable. The Hafele-Keating experiment of 1971 further confirmed these predictions. Atomic clocks were flown aboard commercial airliners around the globe, then compared with stationary reference clocks. The results aligned precisely with relativistic calculations. Clocks aboard the planes exhibited measurable differences, having experienced a slightly different passage of time due to both their speed and their position relative to Earth's gravitational field. Such experiments demonstrate that gravity exerts a tangible influence on the passage of time, and that this influence is not merely theoretical, but a factor that affects our technologies and our understanding of the universe. Gravitational time dilation becomes even more dramatic near extremely massive objects. Consider a neutron star, packing more than 1.4 solar masses into a sphere only about 20 kilometers across. In its immediate vicinity, the curvature of space-time is so intense that a second for an observer near the surface might correspond to several seconds for a distant observer. Black holes take this to the extreme. Near the event horizon, the warping of space-time stretches time toward infinity, creating a situation where a falling observer experiences seconds, while the rest of the universe ages years or centuries. This is not science fiction, but a direct consequence of the mathematics of general relativity, confirmed indirectly by observations of objects orbiting these compact bodies. Alternative models of gravity offer additional perspectives on this phenomenon. Eric Verlinde, for example, has proposed emergent gravity, in which gravity is not a fundamental force but arises from changes in entropy associated with the information content of spacetime. In this framework, time itself may also be an emergent property, intimately connected to the distribution and dynamics of matter and energy. While these ideas are still being explored and debated, they reinforce the view that the relationship between mass, spacetime, and time is profound and multifaceted, extending beyond the classical formulations of general relativity. Understanding gravity as the primary factor in slowing time locally illuminates many aspects of the universe. It explains why particles in high-energy accelerators appear to live slightly longer than predicted, why GPS satellites require precise relativistic adjustments, and why distant cosmic phenomena unfold on dramatically different temporal scales from our own. Even within the confines of our solar system, the warping of spacetime subtly affects motion, orbital periods, and the measurement of intervals. On larger scales, gravitational time dilation shapes the dynamics of galaxies and clusters, influencing the evolution of structures across billions of years. The underlying principle is elegantly simple, even if its consequences are counterintuitive. Wherever mass curves spacetime, the flow of time adjusts accordingly. Time is no longer a uniform river flowing identically for every observer. It is a pliable medium, stretching and contracting in response to the gravitational landscape. Einstein's insight transformed our understanding of reality itself, showing that space and time are inseparable, intertwined into a four-dimensional continuum in which every planet, star, and particle participates in a cosmic choreography. Yet even as general relativity provides precise predictions, it invites further questions. How does time behave when gravity becomes extreme, approaching the singularities of black holes? What happens when relativistic effects intersect with quantum uncertainty at the Planck scale? These mysteries suggest that our understanding of time, though advanced, is still incomplete, and that the interplay of mass, energy, and temporal flow may hold surprises that challenge our most fundamental intuitions. In contemplating gravitational time dilation, we can begin to sense the richness and subtlety of the universe. Every second we experience is part of a complex network, influenced by the curvature of space-time, the velocity of our motion, and the gravitational fields around us. Time is not merely measured, it is woven into the very fabric of reality, responsive to the forces and masses that populate the cosmos. From the steady tick of an atomic clock in a laboratory to the extreme stretching near a distant neutron star, gravity governs the tempo of the universe, reminding us that time, far from being fixed, is a living, dynamic quantity, constantly shaped by the structures and motions of the cosmos. When we step into the realm of extreme gravity, the universe reveals some of its most astonishing and counterintuitive behaviors. Black holes and neutron stars are among the densest objects known, warping space-time so dramatically that time itself bends in remarkable ways. A neutron star, though only about 20 kilometers in radius, can contain more than 1.4 times the mass of the Sun. This incredible density creates gravitational fields millions of times stronger than those on Earth, resulting in significant slowing of time for anything near the surface. Black holes amplify this effect to the extreme, creating regions where the very fabric of space-time approaches a singularity, and the flow of time can appear to stretch toward infinity for distant observers. Renowned physicists such as Kip Thorne and Andrew Hamilton have devoted extensive study to these extraordinary objects. Thorne, a Nobel laureate and consultant for scientific accuracy in popular media, has explored the physics of black holes and wormholes, demonstrating how tidal forces and relativistic effects near these bodies would be experienced by an observer. Hamilton, an expert in black hole interiors and the mathematical modelling of their structure, has detailed how event horizons, the invisible boundaries beyond which nothing can escape, serve as markers of profound temporal distortion. Near an event horizon, seconds for a falling observer might correspond to years or even centuries for someone far away, a demonstration of time dilation at its most extreme. Tidal forces near these dense objects are another extraordinary consequence of their mass. A spacecraft approaching a neutron star or black hole would experience a differential gravitational pull between its nearest and farthest points, stretching it along the axis pointing toward the massive object while compressing it along other dimensions. This spaghettification, as it is colourfully termed, illustrates the sheer intensity of space-time curvature. While our minds struggle to picture this, the underlying principle is simple. The stronger the gravitational field, the slower time passes relative to regions of weaker gravity. Causal patch perspectives provide an additional framework for understanding these extreme environments. Each observer occupies a local region of space-time, or causal patch, in which events can influence and be influenced by other events within that patch. Observers near the horizon of a black hole experience time and sequence of events differently from those far away, yet both perspectives are valid within their respective causal domains. This highlights that time is inherently relational. It is not merely an absolute measure, but a property emerging from the network of interactions and positions within space-time. Thought experiments help illustrate these concepts in more tangible terms. Imagine a traveller journeying close to the event horizon of a black hole. For them, minutes or hours might pass, but when they return to a distant location, centuries could have unfolded. Aging in this context becomes a relative experience. The traveller might scarcely age while the universe outside advances by millennia. These ideas, while theoretical, are grounded in precise mathematics and the predictions of Einstein's field equations. They demonstrate that time is not a uniform, universal flow, but a flexible and context-dependent phenomenon, intimately tied to gravity and location. Extreme gravitational environments also provide fertile ground for exploring the intersections of relativity with quantum mechanics. Near singularities, the curvature of spacetime becomes so intense that quantum effects cannot be ignored, raising questions about how time behaves at the Planck scale. Here, classical notions of continuous time give way to probabilistic or emergent descriptions, and physicists like Thorne and Hamilton explore the limits of predictability and the nature of temporal sequences. These investigations suggest that time, far from being a simple backdrop, is intertwined with the dynamics of matter and energy at all scales. Beyond theoretical musings, astronomers observe evidence of gravitational time dilation in action. Pulsars, which are rapidly rotating neutron stars, serve as precise cosmic clocks. Their rotational periods can be measured to extraordinary accuracy, revealing subtle variations caused by gravitational fields and relativistic motion. Observations of pulsars orbiting other dense stars or black holes provide real-world confirmation of the predictions of general relativity. Similarly, the accretion disks around black holes glowing with energy as matter spirals inward allow us to study temporal and gravitational effects indirectly, offering windows into a universe where time stretches and compresses in ways unimaginable on Earth. Even light, which travels at a constant speed, is affected by these extreme conditions. Gravitational redshift occurs when photons climb out of a deep gravitational well, losing energy and shifting to longer wavelengths. This shift is a manifestation of time dilation. As time slows near the massive object, the frequency of light emitted appears reduced to a distant observer. Such effects are routinely measured by observatories like the European Southern Observatory and NASA's Chandra X-ray Observatory, providing empirical evidence that time is profoundly influenced by gravity. Considering extreme gravitational environments invites reflection on the nature of observation itself. Each observer, whether free-falling into a black hole or orbiting at a safe distance, experiences a unique temporal sequence. The local passage of time depends on position, motion, and gravitational potential, reinforcing the principle that time is not absolute but relational. It is a phenomenon emerging from the structure of spacetime, shaped by the distribution of mass and the trajectories of matter within it. These insights carry profound implications for theoretical physics and our understanding of the universe. They suggest that what we perceive as the flow of time is deeply dependent on context and perspective, influenced by forces and configurations far beyond everyday experience. As we contemplate journeys through extreme gravity, from neutron stars to the precipice of black holes, we see time revealed as a dynamic and malleable aspect of reality, stretching, compressing, and weaving itself around the mass and energy that define the cosmos. In these regions, the universe displays its most intricate temporal choreography, offering a glimpse into the fundamental nature of time and the limits of human intuition. Through this lens, every second becomes part of a vast interconnected tapestry, where gravity dictates rhythm and curvature guides the unfolding of events. By studying black holes, neutron stars, and the causal structure of spacetime, we gain not only theoretical insight, but a new appreciation for the subtle, often hidden, ways that time is sculpted by the universe itself. It is a reminder that time, though familiar and intimate, is a cosmic phenomenon, bending and stretching with each massive object, each orbiting planet, and each pulse of energy, inviting us to reconsider the very essence of moments as we know them, As we move from the cosmic scales of black holes and neutron stars to the microscopic world of quantum mechanics, our understanding of time becomes even more subtle and intriguing. In this realm, time may not exist as a fundamental entity at all, but rather emerge from the interactions and relationships between systems. Carlo Rovelli, a pioneer of loop quantum gravity, proposes that space-time itself is composed of discrete loops of quantum geometry, and that time emerges from the correlations among these loops rather than existing independently. In this framework, the flow of moments is not universal, but relational, dependent on the network of interactions within the quantum fabric of the universe. Similarly, Fontini Markopoulos' work on quantum causal histories extends this relational view, suggesting that the sequence of events in the universe is governed by causal relationships at the quantum level. In such models, time is a bookkeeping device that orders these relationships, but it has no independent existence outside of the correlations themselves. This perspective challenges our intuitive sense of time as continuous and uniform, presenting a universe where temporal sequences arise from the structure and connectivity of quantum processes rather than from a pre-existing temporal backdrop. Julian Barber takes this idea further with his concept of a timeless universe. He envisions the cosmos as a series of static configurations, each representing a complete state of the universe. The perception of motion and temporal flow arises from the way these configurations relate to one another, forming what he calls time capsules. In this view, change exists, but time as a separate entity does not. It is an emergent construct, an ordering of states that gives the illusion of continuous progression. When considered alongside the relational models of Rovelli and Markopoulou, Barber's approach invites us to see time as a phenomenon, arising from the patterns of reality rather than as an independent parameter governing it. The Page-Wouters mechanism offers another compelling quantum perspective. Developed by Don Page and William Wouters in 1983, this mechanism describes time as an internal correlation between subsystems of a quantum system. In a global sense, the universe may exist in a stationary quantum state, with no external time variable. Yet, observers embedded within the system experience time through the changing correlations of these subsystems. In essence, what we perceive as the passage of seconds, minutes, and hours is a reflection of how parts of the universe relate to each other, not of an absolute temporal flow. Entanglement further illustrates the relational character of time in quantum systems. When two particles are entangled, the state of one instantaneously informs the state of the other, regardless of the distance separating them. This phenomenon, verified in countless experiments since the pioneering work of John Bell in the 1960s, demonstrates that correlations in quantum systems can defy classical intuition about simultaneity and temporal order. The sequence of events becomes dependent on the observer's frame of reference and the specific measurements performed, reinforcing the notion that time is deeply intertwined with observation and context. Connecting these quantum frameworks to gravitational time dilation, we can begin to see a unified picture of relational time across scales. Near massive bodies, time slows, relative to distant observers due to spacetime curvature, as described by general relativity. In quantum models, the passage of time is determined by interactions and correlations, suggesting that even at the smallest scales, temporal flow is not absolute. Both perspectives point to the same principle. Time is shaped by context, whether that context is defined by mass and energy on a cosmic scale or by entanglement and correlation on a quantum scale. Experimental evidence, though indirect, supports these ideas. Research at institutions such as the Perimeter Institute and the Max Planck Institute for Gravitational Physics explores how quantum states evolve in curved spacetime, seeking to observe subtle deviations from classical temporal behavior. While the direct measurement of emergent quantum time remains a frontier of physics, thought experiments and theoretical models provide consistent predictions. For instance, hypothetical observers near microscopic black holes or in high-energy quantum fields would experience temporal sequences that differ from distant observers, echoing the relativistic time dilation observed on macroscopic scales. High-level concepts like entanglement, superposition, and quantum coherence illustrate that time, as we perceive it, is a product of relational structures rather than a fundamental dimension. A single moment, then, is not an isolated point along a universal timeline but a snapshot defined by correlations between systems. This has profound implications for our understanding of causality, sequence, and even the nature of existence. Moments are not universal markers. They are emergent events arising from the interplay of matter, energy, and observation, just as gravitational time dilation emerges from the distribution of mass and the curvature of space-time. In this light, time becomes a dynamic property of reality, one that exists where relationships exist and ceases where there are no interactions to define it. It is a living, responsive feature of the universe, shaped by the structure and evolution of everything within it. From the smallest quanta to the largest stars, time is not imposed externally, but emerges naturally from the web of connections, correlations, and causal relationships that make up the cosmos. As we contemplate these ideas, we realize that our intuitive experience of a steady, uniform progression of seconds is a simplification, a convenient construct that helps us navigate the world. In truth, time is fluid, context-dependent, and deeply intertwined with both the fabric of space-time and the patterns of quantum reality. It is simultaneously a measurement, a perception, and an emergent phenomenon, reminding us that the universe is far richer and more complex than our everyday intuition suggests. In understanding quantum time and emergent phenomena, we glimpse the universe not as a stage on which events unfold, but as an interconnected, evolving system in which time itself arises from the dance of matter, energy, and observation. One of the most profound insights into the nature of time comes from the study of entropy, the measure of disorder in a system. In the 19th century, Rudolf Clausius formalized the concept of the second law of thermodynamics, observing that in isolated systems entropy tends to increase. This observation provides the foundation for the thermodynamic arrow of time, a principle explaining why certain processes are irreversible. A dropped glass shatters and does not spontaneously reassemble. Heat flows from hot to cold and never the reverse, and, at a cosmic scale, the universe evolves from states of low entropy to ever greater disorder. Entropy gives time direction. It imbues the flow of moments with a sense of past, present, and future. Ilya Prigogine expanded this understanding by examining non-equilibrium systems, showing that order can emerge even as entropy increases. In complex systems, including living organisms and planetary atmospheres, dissipative structures form, creating local pockets of organization while the overall entropy of the surrounding environment rises. These insights reveal that the arrow of time is not only a macroscopic phenomenon, but also a feature of dynamic systems far from equilibrium. Life itself, constantly consuming energy and producing waste, is a vivid illustration of entropy in action, and of how temporal direction emerges naturally from the laws of physics. Modern cosmology adds another layer to our understanding of temporal direction. Sean Carroll, a theoretical physicist at the California Institute of Technology, explores the low-entropy origins of the universe and how they set the stage for the arrow of time on a cosmic scale. The universe began in an extraordinarily ordered state following the Big Bang, and the subsequent expansion and evolution have been accompanied by a gradual increase in entropy. This low entropy beginning is essential for explaining why time appears to flow in a particular direction, why causality is maintained, and why we experience a coherent sequence of events. Without this initial state, the distinction between past and future would be blurred, and the ordered unfolding of the cosmos would be inexplicable. Statistical mechanics bridges microscopic reversibility and macroscopic irreversibility, providing a framework for understanding why entropy increases even though individual particles obey time-symmetric laws. At the level of atoms and molecules, collisions are reversible, and the fundamental equations of motion do not distinguish past from future. Yet, when large ensembles of particles interact, the overwhelmingly probable outcome is an increase in disorder, a concept formalized by Ludwig Boltzmann. This statistical perspective reconciles the apparent contradiction between reversible microphysics and the unidirectional flow of macroscopic time, showing that the arrow of time emerges naturally from the aggregation of countless small events. Entropy is not only a physical quantity, it is intimately connected to perception and experience. The human brain interprets causality, sequences events, and constructs memory in ways that align with the thermodynamic arrow. Our recollection of past events and our anticipation of future ones are shaped by this directional flow, embedding the physical laws of the universe within our subjective experience. In this sense, entropy links the objective evolution of the cosmos to the cognitive processes that define our sense of temporal progression. Moments are stitched together in memory, ordered in accordance with the underlying statistical tendencies of matter and energy, Gravitational fields also influence the perception and measurement of time, intersecting with thermodynamic considerations in subtle ways. Near massive bodies, time slows due to space-time curvature, and the relative progression of entropy can differ between observers at varying gravitational potentials. For example, an atomic clock placed at the top of a mountain experiences a slightly different passage of time and accumulates entropy at a rate slightly faster than a clock at sea level. While these differences are extremely small, they illustrate how gravitational time dilation and thermodynamic principles interact, reinforcing the idea that the flow of time is not uniform, but contingent on both context and perspective. Quantum mechanics introduces additional layers of complexity. In entangled systems, correlations between particles can influence the apparent order of events, while the probabilistic nature of quantum states challenges classical notions of causality. Nevertheless, statistical tendencies toward higher entropy remain consistent, linking the microscopic uncertainty of quantum behavior to the macroscopic directionality of time. The combination of gravitational, thermodynamic, and quantum effects paints a picture of time as a relational phenomenon, one that emerges from the interplay of energy, matter, and observation, rather than existing independently as a universal constant. By considering entropy, irreversibility, and the arrow of time, we begin to understand why the universe unfolds in the way it does. We see that time is not merely a parameter to be measured, but a consequence of physical laws and cosmic initial conditions. The increase of entropy, the formation of dissipative structures, and the stretching of space-time together shape the rhythm of events, guiding particles, planets, and stars through an ordered sequence of changes. This perspective bridges classical thermodynamics, modern cosmology, and quantum theory, demonstrating that the direction and passage of time emerge from fundamental processes across all scales of existence. Ultimately, the study of entropy provides a lens through which we can understand both the objective and subjective flow of time. It explains why the universe evolves from simplicity to complexity, why causality is preserved, and why our conscious experience aligns with the progression of moments. Entropy, intertwined with gravity and quantum phenomena, reminds us that time is not a static backdrop, but a dynamic, emergent property, sculpted by the interplay of matter, energy, and the intricate structure of reality itself. In this way, the arrow of time reveals not only the physical evolution of the universe, but also the deep connections between the cosmos and the conscious observers who perceive it. While Einstein's general relativity has long provided the foundation for our understanding of gravity and its effects on time, the frontier of physics is exploring alternatives that challenge and expand upon this framework. One of the most intriguing proposals comes from Erik Verlinde, a Dutch theoretical physicist who, in 2012, introduced the concept of entropic gravity. In this view, gravity is not a fundamental force, but emerges from changes in information associated with the positions of matter. Space, mass, and energy interact in such a way that the pull we interpret as gravity is a manifestation of underlying entropic tendencies, a statistical consequence of information encoded in the fabric of spacetime. Verlinde's perspective opens fascinating possibilities for time itself. If gravity emerges from information and entropy, then the passage of time may also be linked to these underlying informational processes. Time, in this sense, is not simply warped by mass but is influenced by the statistical mechanics of the universe, with localized temporal flow reflecting patterns of order, disorder, and correlation. This approach suggests that gravitational time dilation, while observable and predictable in conventional terms, might also be understood as a reflection of deeper informational relationships, a bridge between thermodynamics, information theory, and space-time geometry. Lee Smolin, another leading theoretical physicist, has proposed the idea that the laws of physics themselves evolve over cosmological time. In this framework, the constants and equations governing reality are not fixed, but may change in response to the universe's development, a process that can subtly influence temporal flow. If the laws of physics are dynamic rather than immutable, then the rate at which time progresses could vary across different regions of the cosmos or across different epochs of cosmic history. Smolin's evolving laws introduce the possibility that time is not only relational, but context-dependent on the physical rules operating in each region of spacetime, offering a richer tapestry of temporal variability than conventional gravity alone predicts. Not all scientists are convinced by these unconventional ideas, and critiques from thinkers like Sabine Hossenfelder, highlight the importance of empirical grounding. Hossenfelder, a physicist at the Frankfurt Institute for Advanced Studies, emphasizes that while theories such as entropic gravity or evolving laws are mathematically elegant, they must make clear, testable predictions to be scientifically meaningful. Her work reminds us that speculation, no matter how creative, must ultimately connect to observation, measurement, and experimentation, ensuring that discussions about alternative gravity and temporal effects remain rooted in reality. High-energy astrophysics provides an arena where these alternative models may yield measurable differences. In the interiors of black holes or neutron stars, where gravitational fields reach extremes and conventional relativity approaches its limits, variations in temporal flow under modified gravity theories could potentially be observed. Hypothetical scenarios suggest that entropic forces or evolving constants might subtly influence the rate at which clocks tick or processes unfold in these regions. Though direct measurement remains beyond current technology, simulations and indirect observations offer tantalizing possibilities for testing these ideas. Considering these unconventional mechanisms encourages a broader view of how time might behave. In classical general relativity, the rate at which time passes is primarily determined by mass and spacetime curvature. In emergent and relational frameworks, however, time may also respond to information content, entropy gradients, and evolving physical laws. Imagine, for instance, a region of spacetime where the distribution of matter and energy is arranged in such a way that entropic forces accelerate or decelerate temporal sequences locally. While such scenarios are speculative, they invite us to reconsider the nature of time itself as something dynamic, responsive, and deeply interconnected with the universe's underlying structure. These ideas do not replace Einstein's insights, but rather extend them, offering complementary ways to think about gravity and time. Gravitational time dilation remains a measurable, predictable effect, verified by atomic clocks on Earth, satellites, and aircraft. Yet, by incorporating alternative theories, we recognize that gravity and temporal flow may have layers of complexity not yet fully understood. Time could be shaped not only by mass but by information, entropy, and the evolving laws governing the universe. Ultimately, contemplating alternative gravity theories encourages a mindset open to unexpected possibilities. It reminds us that physics is not static but an evolving exploration, where new mathematical formulations, experimental techniques, and conceptual insights continually refine our understanding. Whether considering entropic gravity, evolving constants, or rigorous critiques, the unifying theme is clear. Time is intimately connected to gravity, but it may also emerge from deeper principles, revealing the universe as a dynamic, interconnected system in which every second, every tick of a clock, and every moment of experience is influenced by the fundamental structure of reality itself. The human brain is not simply a passive observer of time, it is an active generator, constructing the flow of seconds, minutes, and hours from the continuous stream of sensory input. Neuroscientists such as Mark Whitman, who studies the role of interoception in temporal perception, Anil Seth, who explores predictive coding and consciousness, and David Eagleman, whose experiments reveal the elasticity of perceived duration, have shown that our experience of time is deeply intertwined with both neural mechanisms and bodily processes. Rather than a uniform river, time is a dynamic product of neural computation, attention, and expectation. At the core of temporal perception are internal clocks and neural oscillations. Different regions of the brain maintain oscillatory activity in specific frequency ranges, such as theta waves, around 4 to 8 cycles per second, and gamma waves reaching up to 100 cycles per second. These oscillations synchronize activity across distant networks, allowing the brain to integrate events into coherent sequences. In effect, these oscillations provide the brain with a framework for measuring intervals, creating a local sense of time that may stretch or compress depending on attentional focus, novelty, and cognitive load. Predictive coding, as described by Anil Seth, further illustrates this process. The brain constantly generates expectations about the timing of incoming sensory events, updating its internal model when reality diverges from prediction. When predictions are accurate, time appears smooth and continuous. When surprises occur, moments can feel elongated, highlighting the malleable nature of subjective temporal flow. Chronostasis offers a striking example of the brain's capacity to manipulate perceived time. Observers fixating on a clock's second hand may experience the first tick after a saccadic eye movement as longer than it objectively is, creating the illusion that time is stretched. Similarly, time compression can occur when events are highly predictable or repetitive, making seconds seem to vanish almost instantaneously. These phenomena demonstrate that our perception of duration is an emergent property, shaped by the interaction between attention, memory, and sensory processing, rather than a direct reflection of objective temporal progression. The brain's construction of time operates alongside physical principles, yet the two are distinct layers of experience. Gravitational time dilation, as predicted by Einstein, alters the flow of seconds for observers at different altitudes or near massive bodies, whereas neural time arises from biological and cognitive processes. Nevertheless, parallels exist. Just as a clock slows near a neutron star, moments can appear longer or shorter to the mind depending on the intensity, novelty, or unpredictability of experiences. The subjective tick of consciousness is, in a sense, a microcosmic analogue of relativistic effects, demonstrating that time can be both absolute and personal, depending on the system observing it. Memory and anticipation also shape our temporal experience. The hippocampus encodes sequences of events, linking them with spatial and contextual cues, while the prefrontal cortex integrates attention and prediction to maintain a coherent narrative of past and future. This interplay allows humans to navigate complex environments, coordinate actions, and anticipate outcomes, all of which rely on a flexible and adaptive sense of time. In high-stress or high-stimulation situations, this temporal architecture can expand or contract dramatically, creating moments that feel stretched into eternity or compressed into a single instant. Even subtle bodily cues contribute to temporal perception. Heartbeat, respiration, and other interoceptive signals serve as internal reference points, helping to anchor the perception of temporal intervals. Wittmann's research suggests that these bodily rhythms are critical for maintaining a sense of continuity, allowing the brain to monitor both external events and internal states simultaneously. In this way, our perception of time emerges not only from neural computation, but also from the integration of sensory and physiological information, creating a layered and multidimensional experience of the present. Experimental research supports these insights with precise measurements. Studies conducted at institutions such as Baylor College of Medicine and the University of Sussex have demonstrated that temporal illusions can be quantified and manipulated, revealing the mechanisms by which attention, prediction, and memory shape duration. By altering the predictability of stimuli or modulating interoceptive feedback, researchers have shown that perceived time can be lengthened or shortened by substantial factors, confirming that subjective time is an active construct rather than a passive recording of events. The interplay between subjective and physical time becomes particularly compelling when considering human interaction with relativistic environments. While astronauts aboard satellites or spacecraft experience time slightly differently due to gravitational and velocity-based time dilation, their brains simultaneously construct subjective time based on attention, prediction, and sensory input. These dual influences highlight that perception and physics operate on distinct but interrelated layers. One is an emergent product of consciousness, the other a consequence of the curvature of spacetime. Together, they shape the complete experience of moments. Ultimately, the brain functions as a temporal engine, continuously synthesizing information to generate the flow of experience. Every sensation, memory, and expectation contributes to this dynamic construction, producing a rich and adaptable perception of time. In recognizing that the mind creates its own internal clocks while the universe provides a physical framework of time, we gain a deeper appreciation for the complexity of temporal experience. Time, as perceived, is not merely measured in seconds. It is actively created by the brain, a product of neural rhythms, bodily signals, and predictive processes, unfolding alongside the broader, relativistic fabric of space-time in which we exist. Certain states of consciousness allow the mind to experience time in ways that seem almost alien to everyday life. Psychologist Mihaly Csikszentmihalyi described the concept of flow, a mental state in which individuals become fully absorbed in an activity, losing awareness of external time. In flow, hours can feel like minutes, and actions unfold with effortless precision, as if the mind is operating on an entirely different temporal scale. Similarly, lucid dreaming allows the dreamer to navigate a fabricated reality with awareness, often experiencing sequences that seem extended or compressed compared to the clock outside the dream. These altered states reveal that subjective time is malleable, dependent on attention, engagement, and neural dynamics. Alan Hobson, a researcher into rapid eye movement, sleep and dreaming, has shown that the brain remains highly active during REM sleep, generating intricate sequences of events that the conscious mind interprets as narrative. Time within dreams can be stretched or compressed, illustrating that the brain's internal clock operates independently from the objective passage of seconds. Robin Carhart-Harris, studying the effects of psychedelics on the brain at Imperial College London, has observed that substances such as psilocybin and LSD can dramatically alter the perception of time, producing experiences in which seconds feel like minutes or entire hours seem to pass in an instant. These findings underscore the elasticity of human temporal experience and demonstrate that the brain actively constructs the flow of time rather than passively recording it. Extreme dilation or compression of subjective time is not simply an oddity of consciousness. It provides insight into how temporal experience emerges from relational processes. When immersed in flow, dreaming, or psychedelic states, the brain may prioritize certain neural pathways and suppress others, altering the perceived sequence and duration of events. This is reminiscent of the relational or emergent models of time discussed in quantum physics, where temporal progression arises from correlations and interactions rather than existing as a predefined universal parameter. The mind's ability to stretch or compress moments mirrors how space-time itself bends near massive objects, illustrating a conceptual symmetry between mind-based and cosmic time dilation. Neuroscientific studies reveal that these altered experiences are linked to network-level changes in brain activity. During flow, regions associated with executive control, self-monitoring, and time awareness show altered connectivity, allowing the sense of temporal progression to shift. Similarly, REM sleep and psychedelic states disrupt the usual hierarchical patterns of neural processing, enabling unusual temporal experiences. These shifts suggest that temporal perception is highly flexible, shaped by the dynamics of neural networks, the integration of sensory inputs, and the regulation of attention and memory. The underlying biological mechanisms provide a bridge between subjective experience and measurable brain activity, demonstrating that time as experienced is both constructed and context-dependent. The parallels between altered consciousness and physical time dilation extend beyond metaphor. In both cases, time is not absolute but relational. Near a black hole, seconds for one observer may correspond to years for another. In flow or dream states, minutes for the conscious mind may stretch into hours or compress into fleeting instants. Both phenomena reveal that temporal flow is contingent, shaped by the environment, the observer, and the interactions within a system. Whether the system is a complex network of neurons or the fabric of space-time itself, these insights invite us to reconsider our intuitions about time. While clocks and physical measurements provide a reliable framework for external events, subjective experience demonstrates that temporal flow is a construct influenced by attention, context, and neural dynamics. In understanding altered states, we see that the human mind is capable of perceiving time as elastic, capable of bending and stretching to accommodate consciousness in ways that reflect the relational and emergent nature of reality. Exploring these states further, we find that they often enhance cognitive performance, creativity, and problem-solving. In flow, individuals can achieve extraordinary feats, guided by the brain's reconfiguration of temporal perception to optimize focus and action. Similarly, dreams and psychedelic experiences can provide insights into memory consolidation, emotional processing, and associative thinking. In all these cases, temporal distortion is not merely a side effect, but a functional component of the mind's capacity to navigate complex information and generate meaningful experience. By examining flow, meditation, lucid dreaming, and psychedelic states, we gain a window into the flexibility of human consciousness. Time is not a fixed external measure, but a phenomenon constructed by the brain in coordination with attention, memory, and sensory processing. These experiences reveal that the mind, much like the universe itself, operates with a local temporal framework, capable of stretching, compressing, and modulating the flow of events. In this way, the study of altered temporal states provides both a deeper understanding of cognition and a compelling analogy for the cosmic bending of time under the influence of gravity, highlighting the remarkable interplay between mind, matter, and the passage of moments. Human perception of time is highly sensitive to environment, and extreme conditions reveal just how flexible our experience of seconds and minutes can be. Astronauts aboard the International Space Station, studied by both NASA and the European Space Agency, provide a unique window into this phenomenon. In orbit, the absence of a natural day-night cycle, exposure to microgravity, and constant motion around Earth all influence temporal awareness. Crew members often report shifts in perceived duration, with tasks sometimes feeling compressed or expanded compared to their experience on the planet below. These observations underscore that temporal perception is not a fixed rhythm but a construct, shaped by attention, context, and bodily cues. Similarly, researchers studying Antarctic expeditions and submarine crews have documented dramatic effects of isolation and monotony on the sense of time. In these environments, days and nights may blend together, and the lack of external temporal markers causes subjective intervals to stretch or compress. Sensory deprivation experiments conducted in both laboratory chambers and extreme field conditions amplify this effect, showing that when stimuli are minimal, the brain recalibrates its internal clock. Subjects often report that hours feel like minutes, or that brief periods feel interminably long, illustrating the brain's role as an active constructor of temporal experience. These human-scale examples highlight a principle analogous to relativistic time dilation. Gravity, motion, and environmental context interact to alter the perception of time. Microgravity experienced in orbit subtly changes the way the vestibular system signals balance and motion, influencing attention and timing. Prolonged isolation alters cognitive processing, affecting memory encoding and expectation, which in turn modulates temporal perception. Even in the absence of extreme velocities or massive gravitational fields, local conditions shape how the brain interprets the passage of time, demonstrating that time is relational and dependent on the observer's circumstances. Studies of temporal perception in extreme environments also reveal how cognitive load and attention influence the flow of time. Astronauts performing complex tasks under constant monitoring, for instance, may experience seconds ticking rapidly when focused on critical procedures, yet feel time drag during periods of inactivity or waiting. Research led by the NASA Human Research Program indicates that these subjective distortions can be quantified, showing measurable differences in reaction times, task performance, and self-reported temporal experience. Such findings underscore the brain's capacity to adaptively regulate temporal perception according to environmental demands and situational significance. Monotony and sensory limitation produce comparable effects on Earth. Submarine crews, sequestered underwater for months at a time, exhibit expanded subjective time, while individuals in isolated research stations in Antarctica experience both expansion and compression of temporal intervals depending on activity and attention. These studies reinforce the idea that time is not simply a linear flow imposed on the mind. It is actively constructed, contingent on sensory input, neural activity, and cognitive engagement. The principle is clear. Without reference points or meaningful events, our perception of temporal progression becomes fluid, much like a river whose current is influenced by obstacles, bends, and the speed of the surrounding terrain. The connection to physical time is striking. Just as gravitational fields warp space-time, producing measurable effects on atomic clocks, extreme environments on Earth and in orbit reshape the brain's interpretation of moments. The mechanisms differ. One arises from mass and curvature, the other from neural computation, but the outcome is analogous. Time is experienced differently depending on context. This parallel reinforces the broader concept that time is relational, whether considered through the lens of physics or cognitive neuroscience. Sensory cues, attention, and internal rhythms all contribute to temporal construction. Circadian cycles, modulated by exposure to light and environmental signals, interact with cognitive and neural mechanisms to anchor subjective time to predictable patterns. When these cues are absent, as in polar winter or microgravity, the brain recalibrates its sense of duration, highlighting the adaptive nature of temporal perception. In some cases, temporal distortion can reach several orders of magnitude, with minutes appearing as hours or vice versa, depending on engagement and novelty. By examining these extreme scenarios, we begin to synthesize insights from cognition, physics, and cosmology. Human perception, shaped by attention, isolation, and sensory input, mirrors the larger principle that time is not absolute but depends on context. Just as clocks slow near massive objects or in motion relative to each other, the brain's internal clock stretches and compresses in response to its environment. These examples provide an accessible, human-scale analogy to the cosmic bending of time, illustrating that temporal flow is always relational, a phenomenon that emerges from the interaction between observer, environment, and underlying physical laws. In considering time under stress, whether in space, under ice, or deep beneath the ocean, we see a striking demonstration of the flexibility of temporal experience. Both the universe and the mind exhibit elasticity, responding to gravity, motion, and context. The lessons from astronauts, polar researchers, and submariners remind us that time is not merely measured in seconds, but constructed through perception and attention, always contingent on location, situation, and the networks of systems, neural or cosmic, that define its passage. Philosophy has long been intertwined with physics in exploring the nature of time, offering perspectives that challenge everyday intuition and even some of the conclusions of modern science. One influential concept is the block universe, which posits that past, present, and future exist equally, forming a four-dimensional space-time structure in which all events are fixed. This idea aligns with eternalism, a philosophical stance suggesting that time does not flow in the conventional sense, but that every moment exists simultaneously, with the experience of progression emerging from consciousness moving through the block. Hugh Price, a philosopher and physicist, has explored the implications of this view for causality and retrocausality, questioning whether effects can precede causes under certain interpretations of quantum mechanics and challenging traditional notions of temporal order. Christie Stoica extends these ideas through quantum space-time philosophy, integrating insights from loop quantum gravity and relativistic physics. His work explores how the structure of space-time at quantum scales may not be continuous, suggesting that the unfolding of events is relational and emergent rather than absolute. In such a universe, time becomes a network of correlations, a framework in which events acquire temporal meaning only through their relationships to other events. This perspective bridges philosophy and physics, showing that temporal order is not merely a measurement imposed on reality, but an emergent property arising from the interactions of matter, energy, and observers. And the philosophical implications are profound, touching on free will, consciousness, and the nature of reality itself. If the block universe or eternalist perspective is correct, then the past, present, and future coexist, raising questions about the nature of choice and the role of human agency. Retrocausality further complicates the picture, suggesting that under certain conditions, what we perceive as present decisions could influence events that are conventionally considered past. These ideas challenge intuitive notions of cause and effect, and invite us to reconsider the relationship between consciousness and the physical universe. Relational and emergent physics complements these philosophical frameworks. In loop quantum gravity, Carlo Rovelli demonstrates that time arises from correlations among quantum events rather than existing as a separate entity. In emergent gravity theories, proposed by Eric Verlinde and others, space, time, and even gravity itself emerge from statistical and informational principles. These models suggest that temporal order is not fundamental, but a construct that appears when certain conditions are met. Philosophical ideas like the block universe and eternalism gain a new dimension when viewed alongside these theories. What seems like a static or predetermined timeline may be an emergent property of deeper relational dynamics, both quantum and macroscopic. The interplay between philosophy and physics also affects our understanding of consciousness. If time emerges from relationships among events, then subjective experience is part of the process, not merely a passive observation. Human perception of flow, sequence, and duration reflects the underlying structure of reality while simultaneously contributing to it. Moments are not just markers along a universal timeline. They are events contextualized by relationships, interactions, and awareness. This perspective reconciles seemingly paradoxical observations, such as the relativity of simultaneity, the elasticity of subjective time, and the probabilistic nature of quantum events. Conceptual frameworks shape scientific inquiry by providing the mental models through which phenomena are interpreted. Considering time as relational, emergent, or eternal influences how we approach measurements, experiments, and predictions. It guides research into cosmology, quantum mechanics, and consciousness, suggesting new hypotheses and experimental designs. For example, exploring how observers experience time differently in curved spacetime can inform both practical applications, such as satellite navigation, and theoretical pursuits, like understanding quantum gravity. Philosophy and physics together create a richer, more nuanced picture of temporal reality, one that acknowledges complexity without abandoning precision. Engaging with these high-level ideas encourages a synthesis across disciplines. By integrating philosophical insights with empirical research, we recognize that time is not a singular, absolute entity, but a layered phenomenon, emerging from the interplay of structure, observation, and interaction. The block universe, eternalism, retrocausality, and quantum relational theories each offer a lens through which the fabric of reality can be understood, and when combined, they reveal that the flow of time, while intimately experienced, is a complex construct shaped by both the universe and the observer. In this light, the passage of seconds, the unfolding of events, and the perception of now are no longer simple notions. They are the product of deep interconnections, bridging physics, consciousness, and philosophy. Time emerges as a relational property, contextual, adaptive, and intertwined with both the observer and the observed. By considering these frameworks together, we see that time is simultaneously measured, experienced, and conceptualized, offering a profound perspective on the universe and our place within it. It is a reminder that moments are more than they seem. Each tick of the clock, each experience, is embedded in a vast network of causality, correlation, and observation, revealing a universe far richer and more intricate than our everyday intuition might suggest. The human mind is not only sensitive to the flow of time, but also capable of constructing it in ways that reflect probability, uncertainty, and complex cognitive processing. Quantum cognition, a field pioneered by researchers such as Jerome Busemeyer and Peter Bruser, applies principles from quantum theory to decision-making and mental processes, providing a framework for understanding how the brain handles uncertainty and ambiguity. In this approach, the brain does not operate with fixed, deterministic sequences of events, but instead navigates a landscape of potential outcomes, weighting possibilities and adjusting decisions based on context, past experience, and predictive models. Central to quantum cognition is the concept of superposition. Just as a quantum particle can exist in multiple states simultaneously until measured, neural representations of temporal events may exist in overlapping probabilistic states before they consolidate into a coherent perception. Interference patterns, which emerge when these possibilities interact, can amplify or diminish the likelihood of certain temporal experiences. For instance, when anticipating an event, the brain may simultaneously entertain multiple possible durations and sequences, leading to the subjective experience of time that is flexible, context-dependent, and often nonlinear. This probabilistic construction of moments mirrors the emergent relational concepts of time discussed in physics, where temporal order arises from correlations rather than existing as a fixed backdrop. Uncertainty, a hallmark of quantum systems, also plays a role in temporal perception. The brain continuously integrates incoming sensory information with expectations and prior experience, generating a range of plausible timelines for events. This mechanism can explain why moments can feel elongated during periods of novelty or heightened attention, and compressed during routine or predictable activity. Just as a quantum particle's behavior cannot be fully predicted until observed, the exact flow of perceived time emerges from the interaction of neural networks, sensory input, and attention, demonstrating the inherently probabilistic nature of conscious temporal experience. These models also highlight the parallels between consciousness-based temporal flow and emergent time in physics. In loop quantum gravity, as proposed by Carlo Rovelli, time is not fundamental, but arises from the relationships between quantum events. Similarly, in the brain, time emerges from the relational patterns of neural firing, oscillations, and network interactions. Both systems suggest that temporal order is a product of interaction rather than an independent entity. Just as space-time curvature around massive bodies slows the passage of physical time, the structure of neural networks and the weighting of potential outcomes shape the flow of subjective time. Neural oscillations, which maintain rhythmic activity across different frequency bands, provide the scaffolding for this probabilistic temporal construction. Theta and gamma waves, for instance, synchronize distant brain regions, enabling the integration of information across space and time. These oscillations act as internal clocks, allowing the brain to measure durations, sequence events, and align perception with action. Yet, unlike a mechanical clock, these rhythms are modulated by cognitive and environmental factors, introducing flexibility into the perceived passage of moments. Attention, expectation, and novelty can accelerate or decelerate these internal clocks, producing experiences that stretch or compress seconds in ways that are measurable and meaningful. Experimental evidence supports the probabilistic and flexible nature of temporal perception. Studies at institutions such as Indiana University, where Bussmeier and collaborators conduct research, demonstrate that human decisions often violate classical probability rules but align with quantum-inspired models. For example, the order in which choices are presented can change the probability of selection, an effect that has direct parallels to interference in quantum systems. These findings underscore that the brain constructs time and decision sequences in a manner that is inherently context-dependent and relational, much like the emergent temporal structures predicted by modern physics. Considering consciousness in this way also invites a re-examination of uncertainty, causality, and temporal experience. Just as quantum mechanics challenges classical notions of determinism, the probabilistic nature of cognitive time reveals that subjective experience is not strictly sequential or predictable. Moments are created by the brain as it evaluates, integrates, and prioritizes information, with the perception of past, present, and future arising from patterns of neural activity, rather than from a fixed universal clock. This aligns with earlier discussions of relational and emergent time, showing that the flow of seconds is a property of interaction, whether in neurons or in spacetime itself. The flexible, probabilistic construction of time in cognition also has practical implications. It influences decision-making, reaction times, memory formation, and attention allocation, allowing humans to navigate complex environments where certainty is rare. By weighting potential outcomes and sequencing experiences based on likelihood, the brain generates a coherent narrative of events while accommodating unpredictability. This dynamic framework mirrors the universe's own relational and emergent temporal structures, where time is not imposed but arises from the interactions of matter, energy, and observation. Ultimately, probabilistic cognition highlights the layered nature of time. Physical clocks provide measurable intervals, gravity, and motion shape cosmic flow, and the brain constructs subjective sequences from uncertainty, oscillations, and predictive coding. These layers operate in parallel, influencing and reflecting one another, creating the rich, multi-dimensional experience of time that humans perceive. By studying these processes, we see that time is not a single, immutable entity, but a complex, relational, and emergent phenomenon, existing at the intersection of physics, cognition, and conscious awareness. On the grandest scales of the cosmos, time reveals itself in ways that stretch far beyond human intuition. The universe began roughly 13.8 billion years ago with the Big Bang, initiating a period of rapid cosmic inflation in which space expanded exponentially, stretching distances faster than the speed of light. During this early epoch, the concept of horizon time becomes critical. Regions of the universe that are now widely separated were once causally connected, meaning events in one region could influence another. As space expanded, these connections became limited, creating local patches of spacetime that evolve at rates determined by their own gravitational and energy conditions. Time on a cosmic scale is thus relational, tied to both the structure and dynamics of the universe. Unconventional cosmologists have explored these ideas in ways that challenge traditional frameworks. Fotini Markopoulou-Calamara, for example, studies quantum causal structures that may define time at the smallest scales of the universe, proposing that temporal ordering emerges from networks of quantum interactions rather than existing independently. Lee Smolin investigates the possibility that physical laws themselves evolve over cosmic time, implying that the very rules governing temporal progression may vary across different regions or epochs. Max Tegmark, in developing the mathematical universe hypothesis, argues that all mathematical structures exist, and the universe we inhabit is one realization in which the progression of time is a consequence of the relationships between entities within that structure. Each of these perspectives reinforces the idea that time is not absolute, but arises from relational and structural conditions. Even within our own galaxy, time is experienced differently depending on local gravitational conditions. Stars orbiting close to the supermassive black hole at the center of the Milky Way experience measurable time dilation relative to stars farther away. Clusters of galaxies, with their massive concentrations of matter and dark matter, warp space-time in ways that subtly alter the passage of time across millions of light-years. Observers located in these regions, hypothetically equipped with perfect clocks, would record temporal rates that differ from distant observers in low-density intergalactic space. These variations are not mere curiosities. They illustrate a fundamental principle. Time is local, context-dependent, and influenced by the mass-energy distribution of the universe. The relational nature of cosmic time also intersects with quantum and emergent frameworks. Just as loop quantum gravity suggests that time emerges from correlations between quantum events, cosmological structures can be viewed as vast networks of interacting systems, each generating its own temporal flow. In regions of extreme density, such as near black hole singularities, these flows diverge dramatically, with seconds for a nearby observer corresponding to years for a distant one. This mirrors the probabilistic and relational constructions of time observed in cognition, where attention, memory, and expectation shape perceived duration. Across scales, from the quantum to the cosmic, time emerges as a property of relationships rather than a universal independent backdrop. Cosmic expansion itself contributes to temporal variation. As space stretches, the light traveling between distant galaxies is redshifted, and the rate at which signals are received changes. This stretching is equivalent to a dilation of temporal intervals from the perspective of distant observers. Instruments such as the Hubble Space Telescope and the Planck Observatory measure these effects, confirming that time is not uniform throughout the universe. Even seemingly empty regions of space possess temporal properties, influenced by the surrounding gravitational landscape, illustrating that time's passage is intertwined with the geometry of space-time itself. The early universe further highlights the relational character of time. During the inflationary period, quantum fluctuations were stretched to macroscopic scales, seeding the formation of galaxies and clusters. These fluctuations not only structured matter, but also determined the temporal sequence of events on a cosmic scale. In essence, the emergence of structure in the universe created the conditions for local temporal ordering, showing that time is inseparable from the evolution of cosmic matter and energy. Observations of the cosmic microwave background, the afterglow of the Big Bang, provide evidence of these early processes and the relational patterns they established. Theoretical models extend these insights to extreme scenarios. Near singularities, conventional definitions of time break down, prompting the development of quantum gravity approaches that treat temporal ordering as emergent and observer-dependent. In this context, local clocks and temporal sequences depend on both gravitational conditions and quantum correlations, echoing the flexibility of time observed in cognition and consciousness. The universe at large thus provides a laboratory for exploring the same relational principles that govern subjective experience, albeit on scales millions or billions of times larger. Even within more familiar regions, local gravitational potentials influence temporal experience. A clock placed on a planet orbiting a massive star ticks slightly differently than one on a distant moon, and light signals between these locations are redshifted according to general relativity. These variations, while subtle, accumulate over cosmic distances and timescales, illustrating that no single temporal frame dominates the universe. Instead, time is an emergent property, woven from local interactions, energy distributions, and relational structures at all scales. By considering cosmic time in this relational and emergent framework, we see clear connections to previous discussions of gravity, quantum mechanics, and cognitive temporal perception. Time is not a fixed river but a dynamic network of local flows, each dependent on position, mass, energy, and relational context. Across galaxies, clusters, and near singularities, seconds, minutes, and years are relative, defined by the intricate interplay of matter, space-time curvature, and observer location. The universe demonstrates that temporal experience, whether cosmic, physical, or cognitive, is fundamentally contextual, emerging from relationships rather than existing as an absolute backdrop. Ultimately, the study of cosmological time illuminates the universe as a relational system. From the rapid inflation of space after the Big Bang to the slow evolution of galaxies and the extreme dilation near black holes, time is shaped by conditions and interactions throughout the cosmos. Observers embedded within these systems experience local temporal flows, each valid in its own context, yet all interconnected within the broader structure of space-time. By viewing time through this lens, we gain a deeper appreciation of its flexibility, relational nature and emergence, revealing a universe where the progression of moments is a complex, context-dependent phenomenon that bridges physics, cognition, and cosmology. As we draw together the many threads of this exploration, a coherent picture of time begins to emerge, one that spans scales from the ticking of a neuron to the curvature of space-time around massive stars. Classical mechanics, grounded in Newton's absolute time and Laplace's deterministic universe, provides the foundation for understanding causality, momentum, and predictable motion. It teaches us the principles of measurement, sequence, and duration in a world where forces act linearly and uniformly. From there, special and general relativity revealed that time is not universal, but observer-dependent, warped by motion, velocity, and gravitational fields. Hermann Weyl's contributions to gauge theory and Friedrich Kotler's coordinate systems helped formalize these insights, while experiments such as Haffler-Keating's atomic clock flights demonstrated that seconds themselves are flexible, stretching and compressing depending on context. Quantum perspectives deepen this understanding further. Carlo Rovelli's work in loop quantum gravity and Fotini Markopoulou Kalamara's research on quantum causal histories show that time can emerge from correlations rather than existing as a fundamental entity. Julian Barber's timeless universe and the Page-Wouters mechanism illustrate how temporal sequences may arise from relational states, while entanglement and superposition reveal that events at the smallest scales are probabilistic, intertwined, and observer-dependent. These frameworks suggest that time, far from being an immutable backdrop, is an emergent property arising from the interactions of matter, energy, and observation. In parallel, cognitive science illuminates how the brain constructs time at a subjective level. Mark Whitman's studies on interoception, Anil Seth's work on predictive coding, and David Eagleman's experiments on chronostasis and temporal illusions show that our perception of duration is flexible, shaped by attention, novelty, and expectation. Flow states, lucid dreaming, meditation, and even psychedelic experiences studied by Robin Carhart Harris demonstrate extreme temporal dilation or compression, echoing the elasticity of cosmic time near massive objects. In these ways, consciousness itself acts as a temporal engine, generating sequences and moments that are relational, probabilistic, and context-dependent, much like time in the physical universe. Alternative theories of gravity add additional nuance. Eric Verlinder's Entropic Gravity, Lee Smolin's Evolving Physical Laws, and critiques from Sabine Hossenfelder encourage us to consider that time might be influenced not only by mass and curvature, but also by informational and statistical principles. Gravitational time dilation, though measurable and predictable, may be only part of a broader picture in which temporal flow emerges from deep, structural and relational properties of spacetime itself. Across galaxies, clusters, and near singularities, seconds and minutes are not fixed but respond to context, mass, and energy distributions. The relational nature of time is evident at every scale. Cosmology reinforces these insights. Cosmic inflation, horizon time, and local clocks in varying gravitational fields, explored by scientists like Max Tegmark with his mathematical universe hypothesis, illustrate that temporal flow is relative and locally defined. Observers in different regions of the universe experience time differently, depending on gravitational potentials, energy density, and causal connectivity. Even the early universe, with its low-entropy conditions described by Sean Carroll, reveals that time's arrow is a product of relational interactions on a cosmic scale. These insights dovetail with quantum and cognitive models, showing a continuity from the microscopic to the universal. Reflecting on these concepts encourages a synthesis across disciplines. The flow of time is simultaneously a physical measure, a cognitive construct, and a relational phenomenon. Seconds on a clock, neurons firing in the brain, and the evolution of galaxies all participate in the same underlying principle. Temporal progression emerges from interactions, correlations, and context. By observing how time bends near massive objects, stretches in the mind, and arises from quantum events, we gain insight into the relational structure of reality itself. The contributions of well-known scientists like Albert Einstein, Isaac Newton, and Albert Michelson are complemented by the pioneering work of less-sighted thinkers such as Marcel Grossmann, Julian Barber, Votini Markopoulou Kalamara, and Christy Stoica. Each has revealed a different facet of temporal reality, from mathematical formalisms and quantum correlations to emergent cognition and cosmic structures. Together, their work demonstrates that time is not a singular, absolute phenomenon, but a multi-layered, interconnected aspect of the universe. On a personal level, these ideas invite reflection. Every moment of conscious experience, every heartbeat and thought is part of this intricate temporal tapestry. Seconds are stretched by attention, compressed by routine, and influenced by both internal neural states and the external gravitational environment. Our subjective experience, intertwined with the objective fabric of space-time, offers a bridge between mind and matter, perception, and physics, consciousness, and cosmology. Gravity, in particular, serves as a window into this relational structure. By observing how time slows near massive bodies, how clocks diverge in orbit, and how quantum correlations and emergent phenomena shape temporal sequences, we begin to perceive the universe not as a static stage, but as a dynamic, interconnected system in which every moment is defined by its relationships. Time is flexible, context-dependent, and intimately connected to the structures of both the cosmos and the mind. As we sit with these ideas, a sense of calm emerges. Time is no longer merely a metric to be measured or a line to be followed. It is a living phenomenon, woven from the interplay of matter, energy, information, and awareness. The seconds we experience are not isolated. They are echoes of cosmic evolution, neural dynamics, and relational patterns that span the universe. In recognizing the fluidity and relational nature of time, we find both wonder and reassurance. That every moment, from the smallest thought to the orbit of a distant planet, participates in the elegant, interconnected dance of reality. In this synthesis of mind, matter, and gravity, we see that time is a bridge, linking perception to physics, consciousness to the cosmos, and human experience to universal structure. It is both deeply personal and universally pervasive, a phenomenon that emerges, bends, stretches, and flows according to context, interaction, and relation. By understanding time in this way, we gain not only knowledge but a profound sense of connection, a way to experience the universe as an intricate, living whole where every moment is part of the unfolding cosmic story.